Question 6, part F, asked to use our answer in part E, so this derivative formula here, to find the value of R. Now R is the radius of our cylinder that minimises A. Now A is the surface area of the inner part of the cylinder. And you may be wondering, well, what's the point of that? Well, what if paint was really expensive and the manufacturer needed a set volume but wanted to change the dimensions of the can to minimise the paint required to paint the inside of the can, let's say, or apply some other coverage to the inside of the can. So they want to reduce their paint cost by making the dimensions of the can in such a way that has minimum surface area but still has enough volume. So this radius can either be increased or decreased to minimise the area. So that's the purpose of this. And we need to find the value for the radius that results in the minimum surface area. Now, we could do this a few ways. We could just directly plot this function into our graphics calculator and find the minimum value for A. It might look like this, and we could, where this is the area and this is the radius, and we could find the radius that gives the minimum surface area. However, unfortunately, because that would be an easier way of doing that, the question does ask to use our derivative formula. Now, the key concept for the derivative formula, this one here, is that when dA on dr is equal to 0, so when this equation is equal to 0, a max or min occurs. And to explain briefly why that happens, and I will be briefly because that's about a term's worth of work, but if I was to redraw, so I have surface area of the can, the radius R, this minimum point here is the point that we're looking for because at a certain radius gives us the minimum area. The gradient of this graph at this point will be 0, and the derivative formula gives us the gradient of the graph. If we took this point here, for example, the gradient would be a negative number. If this point, the gradient would be a positive number. But when the derivative is equal to 0, a min or max occurs. So therefore, I'm going to min occurs when dA on dr is equal to 0. So therefore, I make this equal to 0. 0 equals 2 pi r minus 1 million on r squared. And then from here we can rearrange our equation to solve for r. We have one equation and one unknown r. So I'll give myself a bit of room here. Let's get rid of this. Bring this up here. So now we need to solve for r. So we have 0 equals 2 pi r minus 1 million on r squared. I'm going to take this right hand term, negative 1 million on r squared, over to the left and make it a positive. So 1 million on r squared is equal to 2 pi r. I'm now going to bring this r squared up and multiply it by the 2 pi r, so it becomes 1 million equals 2 pi r to the power of 3, because r squared times r is r to the power of 3. And then r cubed, yeah, sorry, I meant r cubed here, I think I said r squared. R cubed will equal 1 million on 2 pi. So I've taken this 2 pi down underneath the million. Therefore, r will equal the cubed root of this. 1, 2, 3, 4, 5, 6. So 1 million on 2 pi. Because to go from r cubed equals down to r, we cube root the other side. And we can use our calculator from there. So set up a cubed root. It's 3 there. Put a fraction inside the square root sign. 1 million, 1, 2, 3, 4, 5, 6, divided by 2 pi is equal to 54.1926. 54.1926. 54.1926, and the units are in centimetres. And the question doesn't specify how to leave our answer, so I'll leave it to 3 significant figures. 54.2 centimetres. Okay, so this is the radius that will produce the minimum inner surface area of the cylinder, while still maintaining a volume of 500,000 centimetres cubed. And that is the answer to part F, question 6.